And we can start recording. Hello, hello. Let's wait 1 more minute or a couple of minutes for your classmates. Mhm. How was your week of exams? Yes, I heard that from the previous section. Mhm. Yes, what exam are you still having? Análisis e Infe. Análisis 3?
Sí, análisis 3.
Okay.
Todavía está pesadón.
Sí. Yes, it's an interesting one. Infe with JJ. Okay. Okay. So, because I'm guessing you are going to be studying all afternoon and evening for your exams, let's start with this thing. Okay. Okay. So as I told you last week, we are going to start talking about live tables, and essentially it's going to be really, well, it's not going to be that long, but we're going to be discussing live tables this morning, tomorrow, and after tomorrow you will have all the elements to essentially work on your submission for March 14, I think. I believe that's the day. So you have 2 weeks to work on all these things, and remember that you have to submit the first draft of your project in a document with graphs, tables, and everything, but in a nice way. So again, this is the first submission, and I believe live tables are a really convenient checkpoint before we continue, and then let's see that we see something is wrong at the end of the semester. No, this is a really good checkpoint. So yes, this is going to be I know you have a lot of things to do, but live tables are more time consuming, but again, you just have to create one, and then everything else is just using the same information and then the same process. There are a few things that we need to change for men and women, but we're going to see those things tomorrow. Today essentially is just learning the basics of live tables, which well, but by the way, I remember, or I am 100% sure that most of you, at least those who were last semester with me, are familiar with live tables. Okay, so there are a few things that are going to help you essentially when building your live table. For some of you who didn't have the actuarial mathematics, don't worry. We were going to work these things as if you didn't have that experience before. But again, for some of you, I will expect at least to remember a few of these things. And again, they are not that complicated, but these are really important for us. So again, why are we going back to live tables? Because we really use live tables. Live tables are really important for me as a demographer, but also in actuarial sciences for insurance, for pension, and for lots of benefits that we are going to be estimating, that you will be estimating once you graduate. Live tables are really, really useful. And we can use them not only for people, but also for animals, for cars, for so many things that, woohoo, Woodlab has paid this month. Okay, I'm happy. Now I can eat meat. Okay, no, sorry. I just got a text from the bank. Okay, so essentially, we're going to be using all these things uh, in, in a lot of contexts, and hopefully, we're still struggling. Well, not struggling. We're still defining your tema selectos, but I believe that one of the most important things that you probably should learn are survival models. And again, they take this idea of life tables and just expand it to so many things, and that is a really important thing nowadays. But again, it's something that if you remember life tables, and then if you remember your statistics classes and regression, it's something that you could learn by yourself. But again, we're still debating on if we are going to include that or not as a tema selector. But again, that that is just my perspective, and we are for, and so we have to discuss these things. But again, last semester we used live tables, but the perspective that we follow was more using some model, right? So use Gomper's model, Mayhem model, the Moab, but again, that was a really crappy one, so we decided that the Moab wasn't really useful. But or I was giving you some information from tables from SOA or tables from Comisión de Seguros y Fianzas, and we were using these things. Okay, so but now we are going to learn how to take our information, the information that you have for your states and that I have for Mexico, and create our own live table with the real information that we have. Which again, for me, is really important, because if you end up working in insurance or in these things, it's always good to have live tables for your experience, and that's the name they receive, like Mexican experience or Baja California experience. Or you can, if you end up working for GNP, let's say, oh, this is GNP's experience, or GNP's. I don't think it's Spanish, Grupo Nacional Provincial. Yes, GNP's experience. Again, if you have information for your population, you can create your own live tables, and then based on that, provide better estimations. Okay, so again, there are many definitions of life tables, but the definition that I think is really the easiest one and actually express everything is life tables are probabilistic models that summarize a cohort's mortality experience. That's it. There are so many assumptions that we're going to discuss tomorrow, and some of them we're going to discuss them this morning. But this is a really nice explanation. So it's just a model that is telling me how mortality is affecting this cohort. And remember that we are going to be working with cohorts that are birth cohorts, essentially generations, okay? And again, this is a definition, and we're going to follow this cohort from the moment they are born all the way until the death of the last survivors. So how are we going to do that? Because we could actually track these people, and they have done it before in many countries. But if you track this cohort's experience, and then the last of them is dead, this information is useful from an historical perspective, but they're all dead now. So again, we are going to see how we are going to track this impact of mortality based essentially on what we call biometric functions or biometric variables that are the columns in our life tables. And they receive this name because they are measuring life, and they are measuring different aspects of life. So yes, that's what we're going to be doing. So the way that we are going to work right now is you should have for your state population, well, mid-year population. And again, whenever I say population, I think this was from last week, but again, this morning, it is important. Whenever I say population, I mean mid-year after 116, and if we are using individual ages after using Karup-King or splines smoothing techniques. So population is after we have done all these things to this population, okay? So which you should have your population for your state. And the reason I asked you from the beginning, get your information for individual ages and also get your information for age groups, is because when we are building a life table, we need the very first age by itself. we need to identify these individuals age 0 because they are really special in life tables. And then for the second age group, we're going to be working is going to be 1 to 4. We usually indicate the value of the group with the first age, but this is population ages 1 to 4. So if you're working with age groups, you don't have these two, but if you're working with individual age, you have 0 and then 1, 2, 3, 4, and you can create these two groups. And then starting from age 5 all the way down, these are age groups, the ones that, again, you already have. You prorated this information, you move this population to mid-year, and then you applied 116. Okay, so everything that we have been doing was essentially to reach this stage when studying mortality. And for deaths, remember that I told you, well, actually that's the way INEGI provides the information. You have deaths for those who die at age 0, and then 1 to 4, 5 to 9. And I just told you, okay, for the standardization, let's merge the very first two groups, but you need to keep 0 and 1 to 4 in separated groups, because we need that information like this. And now that I remember, some of you emailed me during the last week asking me things like, okay, should I prorate my debts? Should I move my debts to mid-year? And my replies were really like, no, 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 all the time. But the thing is, we could prorate, but that is only if we are 100% sure that people without information regarding their age in the number of deaths, that was essentially uniformly distributed throughout life, which usually is not the case. We have very good information for deaths for some age groups, and we have really bad information for, let's say, really old people or men in specific age groups. Like we have people dying with violence and all these things. So since we cannot make that assumption that the deaths that we have with non-specified specified age are uniformly distributed in population or proportionally distributed in our population, we are not going to prorate those deaths. Okay, there are techniques, there are people working on these things, but again, for purposes of this course, we are just going to ignore those without a specified age. And we don't have to take these deaths to mid-year. Why? Because these deaths are deaths that occur throughout all year. So it's not the same as when we had the population, because we know the population was referenced to one specific date. 2000, February 14, 2005, March, October 17, I think. So, and this was the population, and the reason we were moving this population to mid-year was to approximate our person years. But with deaths, we're assuming that we have deaths throughout all the years, so we don't move these deaths. Okay, so and I was just talking like this because I was hoping you were opening your Excel file, because we are gonna start working with that right now. So let's start building our life table. I'm going to work with well, the previous section I used males, so now I'm gonna use women. 2000, yeah, 2000. Women for 2000. That's the life table. Yes, yes, you ignore those for births and deaths, and that's a good thing that you already have your births, because we're gonna use those tomorrow. Okay, let's build our life table. So the first column essentially is X, is age. So 0, 1, 5, 10, and from this point we can just go all the way. My last age group is 100 and older, but if your last age group is 85 and older, that would be 85 would be your last value for X. Okay. Then population between ages X and X plus N. Why did I have this thing that I like to make these things look nice? Okay, so this is the population that, again, you should have. So I have my individual age population. I have them here. Working with women, 2000. So this is age 0. And then I have Where are they? And I'm going to get 1 through 4. So these are the two populations that I got from the individual ages. Starting at age 5, I can use the population that I got after 116. That I don't know where they are. They should be, come on, here. So this is 116, total men, women, 2005 to 9, okay? So this is my population. Okay. Now, according to what I have here, I also need deaths. And these are the deaths that you downloaded from INEGI. Again, we don't do anything to these deaths. So I have mortality here. So I'm working with women, 0, and 1 to 4, and 5 to 9. I have them here. And there we are. Okay. So these are the first 3 columns that we got that we have for our life tables. And the important thing here is that this is information that we actually got from INEGI. And yes, we corrected this information, we moved the population, but again, this is information that we observed from our population. Yes, Pau?
Mau, perdón, fui yo otra vez. Para las muertes de 0 y 1 año, perdón, ¿cómo le hiciste? Ah, pero es que sí viene como dividido, ¿no?
Yes.
Gracias.
Yeah, you're welcome. Okay, so hopefully you are there with me. And well, here all the examples that I work with males for 2000, but again, is the same thing. Now, let's start creating more information or building our life table, or continually building our life table. So this is something that we already estimated for standardization, but we did it for the total population. But now we are going to estimate for each life table for men or for women for different years. So yes, you will have to build your life tables for all these years. Age-specific death rates. So we're going to take deaths, and then we're going to divide these deaths by our mid-year population. And I'm just going to change the notation to this one, because that is actually similar to the one that we already know from actuarial notation, right? So remember that this is the age-specific death rates between ages X and X plus N, okay? So let's include this thing in here. Okay. So I'm just gonna take deaths and then my mid-year population. And then just double click. Again, this has to be similar to the ones that you already estimated for standardization, so it's fine. Something that I like to do when I reach this stage, and again, these are things that we have to be like double check that this is happening. This should behave like this. And actually, I included this in the slides. Let's double check that this has a J-shape pattern for mortality. Again, in log scale, not in the scale that we have, okay? So I am not going to ask you to do this for your submission, but you should double check that this is happening. Again, this is not the scale that we need. If we change this to log scale, it should have this shape. So if this actually has this shape, we're good. Everything looks fine. We can continue working with our life table. If for some reason it doesn't have this shape, we should double check what is happening. And again, this is for people. If for some reason you build life tables for cars, again, this shape should be different, I am guessing, right? So again, for people, for human populations, we know this happens. So this is just double checking that this is actually what we have. Okay. So let me go back here. Okay. So now here is where we have like we're going to take that leap of faith. Give me a second. Yeah. Okay, sorry. So we're gonna take that leap of faith. No, no, no. I just closed the door. He's gonna be crying in a few minutes outside the door, so that's fine. Okay, so let's. What we're gonna do here is we have been estimating our age-specific death rates, and actually all dogs in mine. I don't know what's going on. Okay, we are going to estimate our. We have been estimating our age-specific death rates by using the deaths that we have for 1 year for age groups and the median population. Remember that this is something that I told you. Okay, this is the proxy that we have for our person years lived between ages X and X plus N, which is, this is the notation, NLX, person years lived by the cohort. And this is something that you should do, that you probably remember from last year, but this is the number of deaths that we have from the life table. Again, they are not the same as the number of deaths that we have here, because these are the ones that we have observed that are coming from a population, and these are deaths that I am experiencing in a life table that are coming from, person years lived that are coming from a cohort, from a closed population. Okay, so this is the most significant thing that we have, and it's not that it's not happening. We actually know this happens. So this is observed, or we can call it real, and this is theoretical, whatever spell, or the hypothetical distribution, or the hypothetical deaths that I have for my population. I don't know, everybody decided to make noise. Okay. Okay. Now, can you hear me? I don't like to use headphones, but whatever. Okay, thank you. So we're going to estimate these things. So we have mid-year population, and we know how to get this population, but how are we going to get these two? So we need to remember a few things from applied mathematics, or to define few things from these things. So first, who remembers what is this? Now, wait a minute. No, radix was at age 0. As actually saying, these are survivors at age X, that they come from a radix from L0, that this was our radix. So we were close. Then we had, well, QX, and what was that? What was the Q? Yes, so this is the probability that a person age X dies before age x plus n. I'm going to change this to include this n here. Okay. And if you remember, we could estimate this by taking the deaths that we have from table and the survivors. Yes? Okay. So this is just, again, this works as a review for you, or some of you, and new definitions for for those of you who didn't have this class last semester. Okay. So now what are we going to do? We need to find LX. This is person years lived between ages X and X plus N. Okay. So we're going to plot our survival function. Remember that this is non-increasing function. Last age is omega. And for hx and x plus n, let's assume that I have these two, I can find Lx and I can find Lx plus n. Okay, so I have these two. Now, person years, remember that the meaning of person years is, okay, with how many years of life a person or population at certain age is contributing to my population in general. So when we discussed this at the beginning, I was okay, if you have 100 individuals in your population and all of them survive 1 year, they will uh, they will contribute with 100 years. If I follow these 100 individuals for 2 years and all of them survive 2 years, the person years will be 200 years, right? So of course I know it's not gonna be like this because some of them are going to die, and what I have in my observed population from INEGI, sorry, some of the we have people moving in, people moving out. So this population can increase or can decline depending on several factors. But here I have a closed cohort because we take our radix and we keep track of the number of survivors. And remember, the only reason they can leave my population is because of death. Here, I am ignoring migration because this is the way life tables are built. But again, we could include migration in. Actually, we do it, but for some other models. So I am going to use, instead of my population, the survivors at age X to see how many years of life this group is contributing to my experience of years lived. Okay. So essentially, what this means is the person years lived between ages X and X plus N. If I pay attention to only age X, it would be this much, right? Lx. If I pay attention to this age, it would be Lx plus N. So essentially, what I have here is person years is going to be the this area below this function. Okay, so of course we could use some integration techniques if I have an expression for survivors, but if we don't have an expression, we can say, okay, I have two options. I could estimate the area of this big rectangle here, and then I am overestimating this person just because I know some of them die in this period, or I could go with the small rectangle here and then adding this area over here. And this area, this is the most important thing. And here I'm using a really big, just in this function, I'm using a lot of separation between x and x plus n. But remember that we have 5 years. And one big assumption that we can make is, okay, let's assume this is linear. So we end up with rectangles and triangles that we can, well, I hope you remember how to estimate areas for these two. Okay, so this is an LX. Okay, so let's start with the first option. Okay, using the big one. So that would mean that would be, what is the area for this thing is base times the height. The base is n. The height for this big one is Lx. And then I am going to eliminate this triangle that I have here. So again, base for this is n. The height is the difference between Lx and Lx plus n. And then divided by 2. Okay? So what is this? The thing that I have here in the parentheses. No, it's not. I know that was from my previous one. Sorry, Victor. So what do I have inside, like in the parentheses? So if I have survivors at hx, and then I subtract survivors at hx plus n, what do I have between people surviving at this age and people surviving at that other age? Come on. Exactly. I have deaths. So this is what I have there. Now let's use the other perspective and use the small rectangle there. So the base is the same, but height now is Lx plus n. Sorry, this is a minus. And then I have to add the triangle that I am not accounting for. So again, it's the same thing. The same is the same, and well, the base is the same. The height, same, and the formula essentially ends up being pretty similar to the one that I had before. It's up to you, and it's really, really easy to double check that these two expressions are the same. This and this are the same. It's really a three-step thing that you have to do. Okay, so now I have expression for my person years leave. And what do I need that for? Just remember, I was using this approach to estimate my age-specific death rates. What I have here, that the age-specific death rates were similar to this. By the way, there was a mistake here. Yes, this is n, and this is x. Sorry. So I'm gonna use the first one, but I could use the second one, but it's just more algebra to find this expression for the age-specific death rates. So now, what are we going to do? And what I'm trying to do is to find a way to move from the real observed rates to my imaginary or constructed cohort or hypothetical cohort. So what I'm gonna do this, I'm just use multiplication using the factor of 1. We use that trick all the time, but this one, the one that I'm going to use is this, right? So when I multiply this expression using this one, I can split the Lx and then having one here, another one here. And remember, number of deaths divided by survivors is my probability of dying. And down here, I just have this Lx going away with this. And then I have, again, the number of survivors down here, okay? So this is a really nice trick, because by doing this, essentially what I am achieving, or where I am getting, is, well, let's ignore that this is an approximate, but it's, let's just use the equal sign. I am moving from reality to hypothetical populations, okay? So here I have one way to move from a cross-sectional analysis to a longitudinal analysis by just clearing the expression for a probability of death. So these two expressions are the same. We could use either one of these and we will reach the same things, because here I'm just using the factor of 2 to get rid of this fraction. But sometimes we actually need that fraction. So I am going to be working with this first one, but you could work with the second one. So before we move forward, what we are doing here essentially is the following. Let me try to get a nice Lexis. And again, let's assume that these are perfect. This is a perfect grid. I know it's not, but okay. So let's say that here we have the year 2000, the one that I'm using right now. So when we have age-specific traits, actually what we have is all this area. This area is what we have for this, right? Because I have deaths, I have population, so I can estimate these rates from here. So what we are doing actually by using this expression is, okay, well, I don't want that. I want to track a cohort throughout life, and I want to have the information regarding their mortality experience. So I'm essentially estimating this thing. So by doing this approximation, or everything that we have done so far, we are moving from having this information in a cross-sectional perspective to a longitudinal analysis from the observed population to my hypothetical cohort. So that's what we are going to do. So we are going to assume, and this is one of the most probably the weakness. No, I don't want to say weakness, but the most strong assumptions is that I am going to assume that the mortality that I have right now can be used to express the expected cohort experience for this generation. Okay, so that's what we are doing here essentially by equating death. Well, not equating, but using this expression from death rates to probabilities. Okay, so okay, let's use these formulas to estimate our next age group. Just give me a second. Okay. So let's go back to the Excel file. And we need n. N is the length of our age interval. So sometimes it's not really necessary, but I think at the beginning, when you're starting with live tables, it's better to have this information here. So n for our first age group is 1. That's the length of age 0. Then for the second age group, we have a length of 4, and then 5, 5, 5, 5, and this was funny. No. For most of these groups, with the exception on the last one, because the last one is 100 and older, or for some of you, 85 and older. So we don't know the size of this last age interval. There are techniques to estimate that, but again, that's not the idea in this for live tables. Okay. So now that we have our column n, we can actually estimate the column for our probabilities. Okay. So I'm just going to follow the first formula here, but actually in the example here, I'm using the second formula, but you reach exactly the same probabilities. Okay, so we go back here. So it's n times the age-specific death rate. So n times this rate divided by 1 plus half of n times the same rate. Okay? Hmm? Wait a minute. Yes, everything is fine. Hmm? Okay. And we can double click in this. Says, okay. So at the beginning, it's going to be really similar, but then we're going to start having differences with when we move in the age, well, in our age groups. So what happens here? We didn't have the value of n, so that's the reason this is resulting in a 0. But what value should we, or what value are we supposed to have in this last age group for the probability of dying before reaching the following age group? Exactly, it's 1. So we really didn't need the value uh, of n because we know the last probability should be 1. Okay, so again, it's always a good idea to double check what's the shape of these probabilities. And not surprisingly, the shape should be pretty, well, it should be the same general pattern as we have for our age-specific death rates. Again, is with the shape of a J. And yes, depending on what was your last age group, you can see a big leap at the end, because remember that we are forcing this to be 1. So that's the reason this is happening at the end. But again, if you didn't get this from your for your probabilities, something is wrong, and this is a good moment to double check everything that you had done so far. Okay? So now we have our probability of death. Again, this is something that uh, we already discussed, blah, blah, blah. Now let's work with our survivors. LX. And LX is the number of survivors at exact age X. Remember that we start with one value. The first value that we use, that we call the radix, is whatever value we want. We usually go with 100,000, but we can use 1 million, 10 million, 1, any 10 to any power. Essentially, that's the standard. But again, I could start with 245,023 for, I don't know, whatever value I can come out with. But again, why? No, so we usually start with 100,000, 10,000, or 1 million. But again, any value for 10 to the power of any integer number, that would be fine. Okay, so let's stop there, because we have, again, this is called the radix, which in this scenario is 100,000. Okay. Now let's continue building our life tables, because in order to estimate the following value for LX, we need those who died, right? Remember that in the previous, when we were moving from rates to probabilities, uh, we we had that this was the expression. So essentially, I'm just moving this to this side and then the number of deaths to this side in order to estimate the following value for survivors. So I need the number of people who are dying. And I know how to get that, because again, I just had from one previous slide that I use this value. Again, I can just move the survivors to this side of the equation, and then I will have those who died at one specific age group, right? So I'm just going to input here death. So it's going to be survivors times probability of death. Hmm? I don't like decimals in these things, but again, you can use 1 if you want to. Sorry, do you have any question? I kind of heard a microphone. Okay, that's fine. And now that we have this value, this number of deaths, we can get the following value for survivors, taking the survivors that we had before and subtracting the number of deaths. And then the same thing for here. And we will get our values for survivors are for deaths from table. Okay. Mm-hmm. And again, something that you have to double check, these two values at the end of the table, they should be the same, because what this means is that, okay, I have almost 4,000 survivors. How many of them are supposed to die in that last age group? Well, all of them. So again, this is something that we can double check. And if we have a different value there, again, something is wrong. Okay. Probably we forgot to put the 1 here, and this is where actually this is what happens. Is like, okay, I didn't, let's say that for some reason I continue with 5 and I ended up with this. Like, these are not the same. So where was my mistake? Okay, probably here. Why is this not 1? Because I forgot to input the 1 and then I didn't need that. Okay, so, and again, these are, I am making emphasis on these things because these are the things that I double about that I check in your live tables, because I know what happened. I usually, I don't know how many times I have taught this class, but I know where uh, what I know the most common mistakes in these things. Okay, so we have survivors, we have people dying. We could get the probability of surviving, but again, here we are just concerned about those who are dying, so we don't need the p for this thing. Okay, now person years lived, and it's not that I am going crazy, but we actually need this value. Okay, the assumption that we followed before was, okay, I want to move from rates to probabilities. We did it, but now I want to estimate the real value for person years. And it's going to be clear in a couple of series after this. So I'm just going to use the first expression that I had. Remember that we have two, and you will reach the same values, okay? So what I'm going to do for these person years, and this is person years between ages x and x plus n, okay? So essentially, with how many years of life these 100,000 individuals are going to contribute to my population during 1 year, because this is only for 1 year, okay? So I take, according to my formula, is n times the number of survivors, and then I subtract those that died times the period they were exposed to death, okay? And again, it is less than 100,000. Why? Because I know some of them died during this first year. Okay. So again, this is the contribution of this 100,000 person my cohort during the first year of life. Okay. And since I have everything there is fine, I think I can double click here, and we reach another problem at the bottom of our life table. Okay. And before going here, just remember this is because before somebody was asking me, what is the meaning of this? Okay, I told you with this 100,000, but let's pay attention to this the 95 to 99 age group. So I have 9,414 survivors in this age group. And the person years that they are living is 33,426. So again, this is the contribution of all of them. What if all of them survive for 5 years? Then they should have contributed to my population 47,000 person years. But they didn't survive these 5 years. They only survived, well, some part of the interval. So that's the reason I only get 33,000. Okay. So how do I get the person years for my last age group. Because the reason here, the problem that I have here is I don't have a value for n. And I know these 3,900 individuals are going to contribute in a number of years. Okay, so how do I get this? Well, I just need to think, okay, what do I have? What expressions do I have for this where I don't need the value of n? So even if I use the other expression, let's say um, the other expression that I had before, I have the same problem. I need the value of n here and here in order to estimate this. So this is not working. Uh, what other option do I have? Let me go back here. No, no. Um, these are the expressions that I just used. No. Ah, look, I have this. And here I don't need the value of n. So I think this is not that I think. This is actually the one that we're going to use. So let me go back all the way down here and say, okay, I know that this age-specific death rate was, sorry, I got it like this. So this means that I can get my person years for this last age group as this. And here I really don't need the value of n because this n is just an indicator. It's just telling me the length of my interval. But what I have here is, okay, my person years for my last age group, so 100 and plus whatever, is going to be those dying in that age group, then the age specific death rate for them. And I have these two values, right? But we are going to use this only for the last age group. For all of the other age groups, we should use this long expression. Okay, I can fix this. So number of deaths divided by the age specific death rate. And then I don't need the red color there. Okay, so what do I need these person years? I have, with these person years, I have contributions. Again, from this cohort, as they survive to each age group, I have the number of years they're actually living. They're giving or they're providing to my population, right? So this is a way of telling me, okay, so how much time they're living or what's the impact of the mortality for every single age group, which is nice. But what if I want to ask, okay, so in total, how many person years is or will an average individual, not an average individual, this population from age X to the end of the life table is going to provide? Well, this is just the explanation for the previous slide. So let's define this following biometric function. I am going to estimate the number of person years lived essentially from here, the number of person years lived from age X until the extinction of population, meaning from age X to age omega. Okay? So how am I going to do that? Here I have omega, I have my survival function, and we're gonna, I think we will have time to review the shape of all these things. Okay? And what I have here is, okay, x plus n, x plus 2n. So this is person years between ages x and x plus n. Then here I have person years between age x plus n and x plus 2n. Yeah, whatever. And then I have this. So if I want to get this number of years, it's really easy. let's, sorry, yes, add all these things starting from this age to h omega. And this is the way we express this function. So Tx is the number of person years that a population are surviving or providing from hx until omega. And you probably remember this from last semester. This was the future lifetime, right? So this is just a different perspective. So for me here in demographic perspective is yes, the number of person years, yes, all the years that these people are surviving. But last semester was okay, the future lifetime for all my population. So how many years do they have of future life? Which again is just that's just the actuarial perspective. So this is easy to estimate because for the last age group, let's go back all the way here. Let's no. Here I don't need the n because I don't have the length of the interval. So if I'm going to add like age specific, person years for per age group, from that age to the extinction of the population, the last one has to be the same, right? So these are the person years these survivors are going to live until the extinction of the population. So the last one is easy. The previous one is okay. So this many years plus what I already have accumulated or what I am expecting to live if I survive to the following age group. And for this one, okay, so this plus what I have in the following cell. So I can copy this go all the way up here. And we reach this nice number. So I end up with 1, 2, 3, 4, 5, 6, 7,754,007 person years. So what do I need that for? So this is the total number of person years, the total number of years. This population of 100,000 is going to actually live from, well, if I start in this at age 0. So these are the number of years they are going to live from age 0 all the way until the last of them dies. Cool. Now what can I do? What do I need that for? Well, we have all this huge number of person years. And let's take this number of person years and allocate this to all my survivors. So essentially, what we are saying is, okay, let's take all these person years and see on average how many person years I'm expecting a survivor to this age will live. And that is the definition of life expectancy. Well, this is complete life expectancy. So we can, so we're going to take all these 7.7 million person years and then divide by the survivors that I have. And by doing this, I get my life expectancy. Here, this first one is at age 0. So a person age 0 who, again, was born in the year 2000, a woman in the year 2000 who's age 0, is expected to live on average 77.5 years. And then a person of age 1 in the year 2000 is expected to live on average 77.8 years. So it went up 0.3 years, which is not small. But the reason for this is since we have really high mortality during the first year, it's not that uncommon for this life expectancy to increase for the first year and then starts going down. And this is what we see going down. Okay. So everything that we have done before was was in order to reach this indicator. And of course, if we are going to be working in insurance, probably we don't need this. We only need these values, right? But what if we want to estimate life expectancy? Or why is this important? Because okay, let's say we're working on pension plans, age 65. How many years on average I am expecting a person who's age 65 in 2000 to live? Well, almost 19 years. So this is important because I need to get enough money to pay these individuals a pension for 18.9 years. Okay, so this is the first approach to all the approach that we're going to use in this course for life tables. Okay, did you get, well, were you following me? Because I was assuming that you were getting all these things at the same time as I was getting there. Okay, now of course if you're working with your states, you're going to get values that are higher or lower than this life expectancy. But be careful because in the previous section somebody told me, okay, but at age 100, I am getting 20 years of life expectancy. Okay, something is wrong. There's no way you can get that. And yes, something was wrong. And life expectancy at birth should be, yes, for these are for women. For women, for some states, actually, you can get 80, but again, it has to make sense. Like if you have Guerrero, Oaxaca, Chiapas, there's no way you get a higher life expectancy than this for women in the year 2000. And again, it's not that you're going to get a really crappy one, but it should be like 76, 75, or things like that. Okay. So again, most life expectancies in Mexico are between 74 and 77.1. Okay, that's a good one. But what we're going to do tomorrow, this is the first life table, which is nice. I like it. I have been doing these life tables for more than 20 years now. And but there are some things that are wrong in this life table, and we are going to fix those things tomorrow. But again, there are going to be things that we're going to fix really quickly. We are going to work on some corrections, and we will end up with a really nice life expectancy estimation. Okay, and of course you have to do this for men, women, 2000. Yes, in this same table. Mhm. So save that table, or if you want to start building your own life tables, you can create your. For instance, this is for women in 2000, and in the previous section I did it for men in 2000. But actually, I already have all my life tables here. Mhm. But again, I could take any of these life tables and then work with them. But again, I think I'm gonna save this one, and tomorrow we're going to fix it. But if you want to start working with your life tables for all these years, it would be nice because we need to reach this stage and then working on the corrections for all life tables. We're gonna change a few formulas in this thing, but not too many. So, um, okay, we have time. I was about to finish and this. This is the way it looks. This is for men in 2000. And again, if you make your life table for men and women, men always have a lower life expectancy or a smaller life expectancy than women. If you get the opposite in Mexico, something is wrong. If we are in a country where we know there is genital mutilation for women, that we have all these things, that could happen. But in Mexico, there's no way life expectancy for men is higher than for women. So these are the checkpoints that we need to be doing. And just for you to have well, as I show you, I already estimated all life tables, and these are with actually with the corrections that I already included, but these are the life expectancy that we have for different years for men and women. And this is life expectancy at birth, essentially for the very first year. And this is the general pattern that we see. Since we reach a really high life expectancy, And again, you can go online and try to find the highest life expectancy. You're gonna find it in Japan for men and women. Well, for the total population and for men, but for women, sometimes it's Japan. Sometimes, do you know what other country or what country has the highest life expectancy for women? Because Japan makes sense, right? We know about Japan, all population in Japan, but for women or any other country that comes to you to your mind when you're thinking about these things. Well, yeah, well, okay. Yes, the blue. I think I call blue spots or whatever. Yes, but that those are for specific regions. But when we talk about national level, there's also one in Costa Rica. But national level, actually, you were not that far. It's Spain. Spain, a few years, life expectancy for women in Spain was higher than life expectancy for women in Japan. And then Japan goes up, and then Spain goes up, and but only for women. For men, Spain, well, the life expectancy in Spain is not that high. It's not low, but again, it only happens for women. But yes, and even if you go to those countries, you're gonna find life expectancies being 83, 84 years. It's not that the big such a big difference. And I think now they were 89. So yes, it's almost 10 years more than the values that we get. But since we reach high values, now the increases that we can have are really small. Again, it's not the same as moving from really high mortality. Like there are still countries that where life expectancy is 43 years, 45 years. So of course, for those countries, making improvements, an improvement is going to be really relatively easy. So the life expectancy will increase. But since we reach kind of a plateau in these things, it's complicated. But this is useful because we can see different things. For instance, what happened here? Hmm? Because we have the total life expectancy was 75 years, 75.1, 75.1, 76. Okay, we could say, okay, there were no improvements in life expectancy between 2005 and 2010. But when we pay attention to women, 77.4, 0.5, 0.9, we were increasing. So that means that for men, actually life expectancy went down between 2005 and 2010. And the reason for that was the period when, well, in 2006 was when Calderon won, and that was when he declared the war against narcotráfico and the drug cartels and all these things. And lots of men died in those years. So we can see the impact of those things. Well, it doesn't look that significant with 0.4 years, but it is something significant. So yes, there was a consequence of that, and then it kind of it's not that nobody's dying now, but it's more, well, it's more standard, let's say. So now the increases are still we went back to this. So and something important here, and I don't know if I mentioned before, this is the life expectancy. Men born in the year 2000, well, the number of years a man born in the year 2000 was expected to live if, and this is important, if mortality conditions stay the same or remain constant, which we know is not going to happen. We would expect mortality to improve, and we would expect a lot of things going on. So chances are that if we actually track this cohort, the 2000 cohort, throughout all their lives, and then we estimate the life expectancy or the average number of years they lived, is going to be higher than this. But this is what we have. This is, again, if we assume that mortality is going to stay the same or remain constant or whatever, this is the expected number of years this person will live. Okay, and of course, this is not going to be the real value, but it's a really good uh, approximation that we will have, or a good estimate that we have. Okay, so just before we go, here are a few things that it's always nice to plot. This is for men between 2000 and 2015 every 5 years. I just click on the smooth thing on Excel. I am not using any fancy smoothing technique here, but this is, again, the shape that we know mortality follows, with high mortality, well, probability of dying at the beginning of life, then going down, we have this bump during teenage, and as you can see, is really more significant between in 2010. So this was again all the violence that it's always there, but in 2010 was more predominant, this impact, and then we have this like constant or linear increase. For women, we have something similar. Bump is not that significant, but we see something like that. Survivors, you should be familiar with this. Well, those of you from actuarial mathematics last semester, this is the general shape of a survival function. Remember that we start, well, in that we were starting in 1, but doesn't matter. We have 100,000, and this goes down, is a non-increasing function, and when we reach h omega, we should reach 0, so somewhere around here will be the 0. So we can see this uh, small change in mortality. And for women, we see, well, I think for men, as you can see, it comes down and is like declining really early. For women, it stays high for more time, and then it declines at this stage. And this is just the number of deaths from the table. And we can see that deaths are concentrated. Yes, we have a few deaths here, but deaths are concentrated around this age. And actually, and this is the last thing that we're going to discuss, there are some people working on this thing. This is from 1950 all the way to 2010. This is for men. I didn't include the 2020 because we don't have the information from that. But this is really a really nice thing, because yes, if we can model this number of deaths into, like, we can split this function into parts. What is happening before age 10, and yes, it is clear it's coming down. And then if we pay attention to the second part, there are a lot of people, and especially again in Europe, because they are way more advanced than us in this thing. The darker it gets is the more recent information. What they are doing is they are studying what we call the compression of mortality. So essentially, before, if you pay attention to the light colors, mortality was really spread throughout life. And as we move in time, uh, we start finding this compression. So deaths are more concentrated around certain ages, which makes sense. We are becoming an older society, and this thing it tends to get more and more compressed. So it's not only that it's getting compressed, but it's only moving towards older ages. And there are people doing research or trying to model this, and this has an impact. I haven't seen anyone from actuarial sciences actually using this for, let's say, okay, what if instead of using life expectancy or these probabilities, I can model where I am expecting, I don't know, this is not a normal, but probably with a t distribution or something like that. Well, assuming that this is a symmetrical distribution, what if we try to model the expected value and the standard deviation around uh, the mean value for this thing? And probably that would result in a really nice or better estimation of the provisions that I need to have as an insurance company to pay pensions. Okay, so again, these are just ideas that we can develop, but it is really interesting to see this compression of mortality. And again, every year or every time that we get new information, we will see this being more compressed, and again moving to older ages, which I think is a really nice thing to see. Okay, so questions uh, regarding life tables? Well, the first approach to life tables, and yes, that's the last one.
Mau, yo tengo una pregunta.
Sure.
O sea, ¿nos conviene ya hacer todas las tablas como la que hicimos hoy o esperarnos a mañana porque la vamos a modificar? O sea, no sé
Uh,
si adelantar o a lo mejor voy a
uh,
moviendo todo.